will present and showcase how NXP is using our solutions in the development and design of electronics and casings, I presume.
So, welcome everybody. Yeah, if I would have known the screen was so big, I might have made different slides. Last time we were here, we had a small screen, right? It is, let me see. Beetje dichter zo, ja? I'm not so used to talking to microphones, to be honest. Yeah, so I'm here representing NXP, but I'm actually also representing this project called Compass. Compass is a European funded project and I'm the project leader. So it's a bit about both, right? What NXP is doing within this project. So first of all, the project itself with all the partners. So it's a European funded project. We have partners in Belgium, so we have some competitors, right? Also in the project from Hexagon, we have Siemens Software there, working with KU Leuven. Then we have partners in Germany, and then on the far right we have partners in the Netherlands. And there it's set MSC Software because that's the legal entity that's taking part of the project. But of course we know that is Hexagon behind it, right? So this is what it all started with, and this is something that is from a project that is was about 25 years ago, or maybe even longer, from the early 1990s, and this is about thermal modeling. And as you all know, I think microelectronics, when it gets too hot, it will eventually fail. That was one of the first key indicators of the reliability of microelectronics, especially if you have something standing on your desktop. That's basically the only thing that can happen, right? Things can become too hot. It's different than handheld devices, which we see around here today also, right? So you want to make simulations of the temperature distribution, and what people then earlier on figured out is that instead of doing this big full finite element model with hundreds of thousands of nodes, I think at that time, you can just represent that with a thermal resistor network. I think we have a pointer in here. That's too small. But the picture in the middle, the graph is just a thermal resistor network, and you can use that fitting routine to fit that on an outcome of your full finite element simulation. I think nowadays we would call it something like machine learning, but it's just basically fitting, right? So then, about 10 years, a bit less than 10 years ago, we were thinking, well, it's nice, we have this for thermal situations, but nowadays, as I said, you use electronics a lot, handheld, you use it in cars, you use it everywhere, and you get a lot of mechanical fills as well. Mechanical robustness is becoming more and more important. So can we have a similar kind of compact model, reduced order model for a mechanical situation? Now, I always say mechanical simulations are more difficult than thermal simulations, to tease us in the team a bit, right? But of course, for mechanical simulations, you encounter different challenges than for thermal. I will come back to that later. So first a bit about the background, what I said about robustness, mechanical robustness. So here you see a kind of classic situation we're continuously dealing with. So on the left you see a schematic, a cross-section of a PCB at the bottom, and on top of that you have a microelectronic product, a simple product, and it's connected via solder buns in the pinkish color. Now these two materials have different CTEs, and when it starts heating up, again the thermal part, right, you have some heat dissipation, it heats up, or you have environmental heat, right, because you use the different temperatures, you start stressing the solder buns. Just because thermal mismatch, you start shearing it. And eventually you will end up with this bottom picture and it will fail. And of course, you don't want a failing device, so you want to do a reliability test. Now, the problem we are facing as an industry is that we make a component and our customer makes the PCB. and the customer doesn't really know what is in the product, right? What the CTE of the product is, and we don't know the CTE of this PCB. So how are we going to test it? Well, eventually we just pick some PCB which we think is relevant, and then we say, well, it can have so many thermal cycles, so many expansion cycles, and we just build in a penalty, right? We say, well, if we think in the field it should cover 1,000 cycles, we test it into 1,500 or 2,000 just to be safe. So can we do better, right, in terms of simulations? This is a kind of generic slide. I don't think I have to discuss that for this crowd, but of course if you want to do product development, you need to feed it with a lot of data, right? I think Bernard also talked about that in the earlier session. Now, the solder material is a kind of a very special material. So we actually already use it like before Christ, right? The Egyptians already used some kind of soldering. And now, as of today, we're still not quite clear of how to describe this material in a full finite element model. We still do research on it, right, for already thousands of years. The problem with solder is that it's a typically non-linear material. So it exhibits creep, so you load it with mechanical stress and it just keeps on deforming. I think we have a lot of mechanical engineers here in the audience, right? We know about it. It's strongly temperature dependent also. But another thing, because this holds also for other materials, I think aluminium at higher temperature can do the same, right? Polymer materials can also creep. The problem with solder is that in the solder bumps we are having is that the material is very much dependent on its microstructure. So the solder bump, the schematic I showed on the previous slide, that's made up of a handful of grains. So the grain orientation, these grains are anisotropic orientation, and the boundaries can play a very dominant role in the behavior. And that's something you see on the left slide, on the left graph, which I took from literature. If you have just a rod of solder material, so there you have a bit more grains. But if you use it as refloat, so that's just a temperature profile we give it, right, to make the solder bump. It has a certain behavior, then it's cooled down slowly. If you quench it in water, you get a completely different behavior. That's the top line. So there's a lot of difficulty in describing the solder material. So what do we want to achieve in the project? So we want to do a full finite element model of this component, then reduce it into some kind of compact form by model order reduction, put it in an exchange format so that our customer can use it in a super element and put it back in a 3D finite element model of the whole structure with all the components. And you can also make models for this solder bump itself. So then something about this model order reduction. So I said we're all mechanical engineers, maybe not mathematicians, but I was very amazed by this model order reduction. Because I thought, how can it be I make a model, and maybe a model I started yesterday at 2.5 million elements, right? How can I possibly reduce that to maybe 10 or 20 in and outputs? And then people in the mathematicians say, yeah, and it's still accurate, right? I didn't believe it. So here I show the stiffness matrix, and this is just linear case, but this is just to give you a flavor of what you can do, right? So I think we know that, right? Force times the stiffness is displacement. This is just strings. But many of the forces, the internal forces, they're just zero, because only on the nodes where you apply forces, or the nodes you want to maintain, you have a number, right? And you can just rearrange these matrices, and I give them a bit of a color, and you see how the rearrangement works. So if I say I only want to keep maybe one node or 10 nodes, then they only end up in this FA and the UA for the displacements. And it's just a rearrangement of matrices. And that seems very handy, right? Because I go from a matrix that's 1,000,000 by 1,000,000 to matrices maybe 100 by 100 or so. And then I thought, well, why don't we always do this trick? And then there's a bit the pitfall, or how you say, call it. Normally finite elements, you have, the stiffness matrix is of the form you have there at the left. So it's just a band matrix, and all our finite element programs work that way, and it's easy to solve. If you do this rearrangements, you get with a fully populated matrix. And I don't have numbers with me, but we did studies, right? And we started with a model with element sizes of 100,000s of elements, and then we reduced it to something like a 10 by 10 matrix, 100 by 100. But once you get already with 100 of 100, 100 by 100 matrix, it's already computational more cumbersome to solve that one than just do the band matrix. So you have to keep your IOs in the reduced order model and the compact model to a minimum. If you take too many IOs, it can be even longer to solve it. And that's just because you leave this bandwidth matrix to a fully populated matrix. So how did we deal with that? Well, actually, our products, they come in a kind of classes, right? The one on the right, I showed you on the earlier slide. So you have this kind of solder bumps, right? These small pieces of solder. We have this kind of insect-like of products. I guess those are quite familiar, right? This is what we all started with. And then you'll have a bit in between where you'll have this solder lens. The kind of trick we came up with is not considering the interface between the solder and the components as a fully flexible interface that can just warp and deform freely, but make that rigid. And by making it a rigid surface, you constrain the number of IOs. So instead of having multiple nodes on this interface, you just reduce it to one single node with 6 degrees of freedom. And that makes it much simpler. And I will show you later how we deal with it. Another trick we do in this first generation of compact models is the following. So in the previous slides I said, well, we do qualification tests, right? And then we do so many cycles, and then we want to cover that, and we say we cover the field life with it. And we do that as a component supplier, our customer is doing it, their customer is doing it. It's just done along the whole supply chain, along the whole value chain. But normally in this kind of test, what we do is we put a product in an oven and then just ramp up and down the temperature. But we ramp it up relatively slowly, in such a way that the whole system is just at a uniform temperature. So, and that's important to notice, it's quite obvious to me, but not to everybody, is that during the test, the products are not allowed to dissipate heat. So it's really a uniform temperature we cycle the products at. And if you have a uniform temperature, then actually you don't have to solve for the temperature anymore, it's just a boundary condition. So we have temperature as boundary condition, and we only have to solve for the mechanical part, and then we do that elastically but at different temperatures. So we forget that we have viscoelasticity in the polymers and so on, but we still have temperature dependent material. Then in the end, before I go to the model results, well actually this is already a bit model results, I talked about the solder, right? We want to cover the solder fatigue. And solder is a very difficult material. I hope I convinced you a bit about it. So how do we deal with that in industry? Well, we just take the deformation energy that goes into the solder interconnect, the gray part in the picture. We average the amount of energy that goes into the deformation per cycle, and then we just relay that to experimental data we have. So at the right, you see Weibull plots. I hope that's a bit familiar. This is a normal reliability statistics you do, and you see that for 3 different kinds of products, right? And if you then know for these 3 products what their deformation energy per cycle is, you can just make a trend line. You get a kind of black box model for your damage, or for your damage model. So there's not really a deep physical or chemical understanding of the material in there. It's just a semi-empirical relation. So the first thing we started with is taking the full finite element model. So you see that on the left of a product, and then start introducing these rigid surfaces. So on the top right, you see this damage plot for the full finite element model, and you see the Z displacement. It's the warpage of this component. And then on the right, you see the similar plots, but there we have introduced these rigid surfaces. And then you actually see that for the damage plots, it goes quite well at the boundaries, right? The one in the middle, that's this big metal plane. That doesn't go that well, but at the edges, which are the functional interconnects, these have similar results. And that's a kind of reasonable, because we share the component, and the warpage there is not so important. Looking at the warpage plot, then of course you see that the bottom one, where we introduce rigid surfaces, it stays flat, right? You have a big metal plane that's soldered, you introduce a rigid surface there, so yeah, of course that stays flat. Then of course there's an obvious way of dealing with that, is just introduce a couple of patches, right? A couple of these rigid surfaces next to each other. So at the left you see the full finite element simulation, then introducing one rigid surface for the big middle part. Then if you do 4, the warpage is already getting better. If you do 9, I would say, for an engineer, maybe not for a mathematician, but for an engineer like me, I'm very happy with that, right? That gives a similar trend, similar color scheme. So then we make a comparison between the full finite element model and the reduced model, and you see that you get similar trends and you get similar numbers, right? Maybe we have to recalibrate this damage model again a bit, right, to correct for the different answers, for the different results. But then we are good to go. And that leads me to the end of my talk. So we have now found a way to reduce this full finite element model. We have introduced these rigid surfaces. This leads us to a standard description, right? We can now say, well, if you deliver matrices in this form, you describe the rigid surface, you need to give some position where these rigid surfaces are. You can just hand it over to the next partner in your supply chain, and they can use that in a super element, or like Hexagon is now working on with the FMU interface. For those who are familiar with that, that's working beautifully. And we can have a linear but temperature dependent model with that. So that is what I had to say for today. The project is ending by this year, so then we hope to have the exchange format ready. Thank you for your attention.